Hi, I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Mapped. We'll explore the mathematics of maps, relying on the wonderful book, Mathematics. This book covers a wide range of map-related topics, including some we've done episodes on here, including fractals, graph theory, and gerrymandering. In this episode, we focus on the global issue of turning a three-dimensional globe into a two-dimensional map. So here are three maps that I found online. The first is called a Mercator map, and is the one that looks most familiar to me. The second is a Gall-Peters map, which looks a little weird to me and has somehow shrunk Greenland and Europe while enlarging Africa. The third is a Robinson map that seems to split the difference between the two. Which one is correct? Well, it turns out that the great mathematician Carl Friedrich Gauss had something remarkable to say about this question in 1827. In fact, Gauss called this his remarkable theorem. Briefly, it says that Gaussian curvature doesn't change with non-destructive manipulation. Okay, well, we can do better than that. Gaussian curvature characterizes how a three-dimensional surface curves. A sphere curves the same way in all directions. If you stand on a sphere, the surface drops off in all directions. The Gaussian curvature of a sphere is positive. A Pringle has negative Gaussian curvature. It curves up in one direction and down in the other. The Gaussian curvature of a flat board or a flat map is zero. The surface does not curve. Since a globe has positive Gaussian curvature and a map does not, the remarkable theorem says we must use destructive manipulation to turn one into the other, i.e. to make the map. We must stretch or tear or in some other way distort reality. Now, since any map will have distortions, the question becomes which distortions are we willing to tolerate? Two properties that are important for maps are shape and size. The Mercator map accurately depicts shapes, while the Peters map accurately depicts relative size. Which one's better? Well, it depends on whether you want, for example, Greenland's actual shape to be correct, or are you more concerned with getting its relative size, not all that large, correct. The Mercator map was first created by Gerardus Mercator, the Latinized name for the Belgian Gert de Kramer. A successful calligrapher turned map maker, he was born in 1512 and lived during an age of European exploration of the world. His quest to make accurate maps was thwarted by wildly different reports of distances by sailors. Mercator eventually determined that the main problem was the sailors' belief that rhumb lines are great circle lines. Now, sailors would be able to maintain a fixed compass direction, that's the rhumb line, to reach a destination. They believed that this took them on the shortest path. Can you see why this is not correct? If you stretch a string along a globe between 2 points, you can find the shortest path, and it will be along what is known as a great circle, i.e. a circle with center at the center of the globe. Look at the great circle arc between Caracas and London and compare the angles made with nearby latitude parallels. They're not the same and are not all that close. To keep a constant angle, your path will have to spiral. Rhumb lines are spirals. Mercator's goal was to create a map on which rhumb lines are straight. In other words, angles are preserved. Going straight from A to B on his map would give the correct angle for navigation. In the process, this means that the shapes of the continents would be correct. Now, how could he do this? Consider a narrow band around, for example, the 30th parallel. On his rectangular map, the band would have the same length as a band around the equator. However, the Earth is considerably wider at the equator, so the rectangular map needs to have a horizontal distance dilation at the 30th parallel. Mercator introduced the exact same vertical dilation to preserve angles. Notice that on his map, the distance between 30th and 40th parallels is larger than the distance between parallels at the equator. So, northern territories, for example, Greenland and Europe, get stretched vertically and horizontally and look much larger than they are. In the 1970s, German historian Arno Peters introduced a map which he intended to correct cultural biases, an enlarged Europe and a diminished Africa, for example, introduced by the Mercator map. His map, which duplicated the work of James Gall in the 1850s, preserves area. If region A looks twice as big as region B on a Gall-Peters map, It is physically twice as big. On a Mercator map, South America and Greenland look to be similar sizes. South America is actually 8 times larger, which is apparent on the Gall-Peters map. Did you know that Africa is so large that it could hold the United States, India, Japan, China, and much of Europe? It doesn't look that way on the Mercator map. Having Europe appear outsized on Mercator's map was accidental and not as blatant as the New Yorker magazine map of the United States. In the New Yorker magazine cover, the Pacific Ocean, Hudson River, and 9th Avenue are all about the same size, and perhaps importance in the mind of a New Yorker. This graphic is, of course, intended to entertain, but images are powerful, and having a realistic representation of size is worthwhile. So, which is correct, the Mercator map or the Gall-Peters map? As Gauss would have explained, neither map is correct. They just distort the globe in different ways. Originally, the Mercator map had advantages in helping sailors navigate the globe. That's not been relevant for many years, so is there any reason other than inertia to keep the Mercator map? Well, sorry, but having grown up seeing the Mercator map, that Gall-Peters map looks a little weird. Now, the following should not rate real highly on anyone's list of priorities today, but the Mercator map does have a nice mathematical representation, which was created in the 1500s and 1600s shortly after Mercator's death. A full description can be found in Mapmatics, but the bottom line is that at latitude A, the distances, both horizontal and vertical, should be stretched by a factor of the integral from 0 to a of the secant of x. Okay. And even more confusingly, that can be shown to be equal to the natural logarithm of the tangent of a over 2 plus pi over 4. Well, mathematicians were working pretty hard on this problem around 1600. The fact that this could be computed in that pre-computer era gave the Mercator map a distinct advantage, and the fact that it exaggerated the size of Europe didn't bother very many people in Europe. Now, the Robinson map, which does not arise from precise mathematical properties of any type, is an attempt to come close to the shape-preserving feature of the Mercator map and the size-preserving feature of the Gall-Peters map. You might call it the best of our world.